Alright, in this video, we're going to go over section 5.1, Randomness, Probability, and Simulation. So our two learning targets are interpret probability as a long-run relative frequency and use simulation to model chance behavior. So, chance behavior in general, probability, is that it's unpredictable in the short run. However, it is regular and predictable in the long run. An example would be flipping a coin. So let's look at the proportion of heads if we flip the coin. Here we have a situation where we're flipping it 10 times. So our line graph is showing the proportion of times it was heads. So the very first flip, we see that it was heads. Then on the second flip, it was actually tails, so the proportion of heads was 0.5. Then on the third flip, it was heads. That's why we have a higher proportion of heads, and back and forth. However, when we look at a situation where we flip the coin 500 times, you see that this line graph is starting to converge just on the horizontal value of 0.5. That's the probability of getting heads, one out of the two chances, but overall, flipping it many, many, many times, you have a probability of 0.5. So, probability is an outcome of a chance process and is a number between 0 and 1. This is inclusive of both 0 and 1. 0 would mean that it cannot occur, and 1 would be it always occurs. It would be the only instance. So probability, based on the law of large numbers, says that if we observe more and more repetitions, like 500 or a million, so to speak, the proportion of times that a specific outcome occurs approaches its probability. So here the coin would be 0.5, approaching the probability of half for getting heads. So there is a misunderstanding that randomness is predictable, but really we can't. Our intuition about chance behavior tries to tell us that, well, because it was heads so many times, it's got to be tails. But that's not true. It's not going to even out, so to speak. Just because I flip the coin 50 times doesn't mean 25 times will be heads and 25 times it'll be tails. We don't know that. But once you get into a very large quantity of flips, it becomes roughly half and half. So the idea of a simulation is to take something like a coin flip, do it over and over and over again to see what the probability of a particular outcome would be. So there are 3 steps to a simulation. First, we need to describe how we'll use chance to imitate a trial run. We'll actually perform a trial, and then we'll use those results to answer the question. So our example here is about the collectible cards of NASCAR drivers in cereal boxes. So in an attempt to increase sales, a breakfast cereal company decides to offer a NASCAR promotion. Each box of cereal will contain a collectible card featuring one of the following NASCAR drivers: Joey Logano, Kevin Harvick, Chase Elliott, Danica Patrick, or Jimmy Johnson. The company claims that each of the 5 cards is equally likely to appear in any box of cereal. A NASCAR fan decides to keep buying boxes of the cereal until she has all 5 drivers' cards. She is surprised when it takes her 23 boxes to get the full set of cards. So our task is, does this outcome provide convincing evidence that the 5 cards are not equally likely? To help answer this question, we want to perform a simulation to estimate the probability, to perform a simulation to estimate the probability that it would take 23 or more boxes to get a full set of 5 NASCAR collectible cards. So the reason, or the idea behind doing a simulation is, instead of going to the store and buying a bunch of boxes of cereal, you just let random and chance play that part to find out what would be the probability of actually going to buy the 23 boxes. So, first step, describing how we're going to use a random number generator to perform one trial. So the first thing you need to do is set up your simulation and say, okay, what are my numbers going to represent? So there were 5 cards, so we're going to use the numbers 1, 2, 3, 4, 5. 1 is going to be the Joey Logano card, 2 for Kevin Harvick, 3 is Chase Elliott, 4 is the Danica Patrick card, and 5 is Jimmy Johnson. Then we generate a random integer. This can be using your calculator, it can be the random digit table. If it's the random digit table, you do have to decide how you're going to do your numbers. Here we have 1, 2, 3, 4, 5, so that means numbers 0 and 6 through 9, what you would omit. Or you can use your calculator. So we're going to generate a random integer 1 to 5 to simulate buying a box of cereal and looking at which card is inside. You keep generating the random numbers until all 5 labels from 1 to 5 appear. Because remember, we're buying the boxes of cereal until we get all 5 collectible cards. So the dot plot shows the number of boxes of cereal it took to get 5 driver's cards in 50 trials. Okay, so explain what the dot at 20 represents. Well, that is one trial where it took 20 boxes to get all 5 driver's cards. Okay, so this right here above 10, 1, 2, 3, 4, 5, there were 5 trials at which once we purchased the 10th box, we had all 5 collectible cards. Part C, use the results of the simulation to estimate the probability that it will take 23 or more boxes to get a full set of cards. 23 or more. So this is 20, 21, that's 22. So 23 or more, there are 0. So the probability that it will take 23 or more boxes is 0. So there's a 0% chance. So if you use the word chance, you're using percents. If you use the word probability, it's a decimal. Chance and probability are different notations of the number. One's a percent version and one is a decimal between 0 and 1. When you're answering a probability question, it's okay to answer it as percent, just make sure you say chance and not probability. So there's a 0% chance it would take 23 or more boxes to get a full set. So the other question was, does this outcome provide convincing evidence that the 5 cards are not equally likely? Well, because it is so unlikely that it would take 23 or more boxes, because we got 0, to get a full set, this result provides convincing evidence that the 5 NASCAR driver cards are not equally likely. This probability is so low, a low probability means convincing evidence. For whatever it is you're looking for. So a low probability means we have convincing evidence against the claim. All right, so from there, we were able to interpret a probability as a long run relative frequency, and we know how to perform a simulation.